to do this on the radio. My name is Ronnie Herron, and this is the SBAU Astro Hour. It's our 278th program for June 22nd through the 28th of 2026 for you guys to learn, and as a public service of our Telescope and Astrophysics Club, the Santa Barbara Astronomical Unit, which has met regularly for years up at the beautiful Santa Barbara Museum of Natural History. First Fridays of the month for our general meeting. Week later, second Saturdays under the night sky for our monthly star parties. And you are invited to come join us, folks. We focus on some awesome stuff out there, and we invite some amazing speakers. Just $20 a year to join a membership, and you might see us just about anywhere out there with the outreach. Our scopes, we put them up, and doggone, it's all it takes is a dark sky. And that's our outreach. We'll talk about that in a minute. These are our topics of this week. Summer solstice occurred over the weekend, yesterday about 1:30, a day after our town's big parade up Santa Barbara Street in honor of it. And the old sun meets its farthest north latitude, which I think is Tropic of Cancer, isn't it? Moon, planet, stars are all lighting up beautifully. Is it possible, gang, we could consider NGC 7000, the North American Nebula, as our nation's 250th birthday sky object? That could be. Gonna run down NASA's highest priority, costliest, and most capable orbiting space observatories. Got a total of 7 out there, and the big HWO is going up in about 10 years. Just searching for other Earths out there, trying to answer old Doc Fermi's paradox. Let's meet the gang in charge, some of whom may have to leave early. The president will be in charge again. Our president of SBAU is Jerry Wilson. Hi,
hello,
Professor.
Everybody. Good morning. Good morning to my sister, Joyce, and my grandkids, Calvin and Riley, and to my wife, Pat.
That's right. His wife, Pat Forgy, joins his own little peanut gallery. We have an awesome outreach guru, Chuck McPartland, who's on the right side of my screen. Chuck takes us out there constantly. He's also married to the best treasurer we've ever had in the club, and the, I guess, overworked merchandise manager, Pat. Telescope lens expert and maker of scopes and guitars. And they tell me an incredible speaker is Tim Crawford joining us.
Enjoying the beach here.
That's right, shores of Ireland or wherever. And he's married to the lovely Karen. Former Westmont science speaker, professor with his own lab out there, and our newsletter editor, Tom Whittemore.
Morning.
Married to Maureen. We always start each show, as we have forever, with good humor stuff. We're back to some Larson cartoons. The Far Side, I think, may be part of this group of 6.
And Bizarro, too.
Yeah. Forwarded silly science cartoons. This is something else.
Yeah, this is one I added.
Okay, I didn't get this one.
Didn't get this.
You want to guide us through this?
This is an example of Riemannian non-flat, non-Euclidean geometry.
It's like a Mobius strip, isn't it?
And it's in that category, but this one has 2 sides, but it has, it's like at 3 a.m. when you're freezing and you're trying to find the blanket to pull it up on yourself and it's all wadded up at the bottom or something.
We all understand now. Yeah, you can take those Mobius. Okay.
Now, some of these may be repeats. I got that feeling as I was going through them.
All right, outreach guru Chuck, you want to guide us through this? What's going on here?
Well, you just got a couple of scientists dressed as clowns, and they're searching for the Higgs boson particle.
You see the dynamite?
The dynamite's by the test tubes.
Yeah, by the test tube rack.
The eyeball is on his shirt, right above that.
I don't see that.
Right there.
Oh,
there.
Okay, yeah, there.
And you got O2 and K2 and the pi.
The pi, yep.
I don't see the pipe.
Those things a Bizarro guy puts in every cartoon.
Yeah. I don't see the pipe of the spacecraft.
Yeah.
Okay, well, that's not Gary Larson, but it's as weird as. Okay, let's try you, Mr. Whittemore, before you leave us. You're checking out early.
Okay.
What's going on here?
So that's another Bizarro, huh?
Yep.
You
So
guys are talking.
sort of a serious guy is asking, how could delicious cookies possibly harm my computer? It says malicious.
Well, I missed that. Okay, now I get it. There's
Okay,
a
space guy is
space
in
guy.
here.
The
There's-
rabbit.
Yeah, alien eyeball down there,
Yeah.
TNT.
And the pie on his shirt.
Pie.
Oh, wow.
Pie.
And the crown way over on the left.
Yeah.
Oh yeah, missed that.
Cookies are the things they throw into little websites you visit.
Yeah,
Little,
Yeah. Yeah.
Well, they store them on your computer to save things like your password or where
I
you've
like-
gone.
Yeah.
I like this one.
all right, then tell us about it, Mr. Speaker, in December. Tim, on the left.
yeah. Hey, who's that? Oh, Mitch the janitor. Well, our first test run has just gotten a little more interesting.
That's really bad.
I remember
That's
that
bad.
one. That's
That
from
was
the
an easy,
80s.
Yeah.
That's from the 80s. That one.
This
Okay,
is
danger.
This is wild.
who is the guy that does these?
Bob's Rent a Time Machine. That's pretty good. It's being swallowed.
Where does it say that? Huh?
It's in the dinosaur's mouth.
Yeah, right
Oh.
there.
There-
Danger
there's-
design.
Aliens are up here.
there's so much in this.
Yeah, this
Yeah.
is the age of reptiles, considered the best age.
It's pretty good.
But
And
this
then
is a, this is a, this is a
and the-
Larson.
And all the different, what do you call them, fins or the scales that on the yeah, those all those little messages are really amazing.
It's a good
It's
freak.
like-
Yeah.
Oh, there we go.
Graffiti.
got-
It's
Yeah,
all
a lot of
graffiti.
graffiti.
You got the one with the sign saying the asteroid is coming.
Yes, that was a good one. That's a really good one.
You know what? The only thing missing is a monolith.
Somebody being scared by a snake.
Yeah.
Slab.
Oh, you missed that one too. There's so many. There's so much in that one.
Yeah.
Wow.
All right, this looks like a teenage alien having
Yeah,
fun.
and a
You wanna
hot rod going by our capsule. Get a Zord.
Look at the face on the guy in the capsule.
Good Lord. Real dangers out there. So Fermi doesn't get his paradox answered, does he? But we're looking.
Oh, I see. The guy in the alien is yelling at him, "Get a Zorb."
Yeah.
Good Lord. Took their parents' machine, their Millennium Falcon, wherever it's based. Took it for a joyride.
I got to see that Hail Mary the other night. Boy, that's a good movie.
Yeah, it is, isn't it?
Yeah,
Oh, is that a science fiction flick?
Project Hail Mary. Yeah.
yeah. It's really good, Ronnie. You get a chance now. It's on the regular TV now.
What's the actor's name? He was in La La Land, wasn't he?
Yeah.
What was his name?
Ryan Gosling.
Yeah, it's it.
Gosling.
Ryan Gosling. It's
I gotta
it's
check.
really good. And then the little alien guy, Rocky.
Okay, my computer has frozen. I'm gonna bail out and come back.
Oh wow, that's
Talk
a
among
little early to
yourselves.
be
It's
frozen, Jerry.
solstice.
And leave us alone? My God, can we do it, gentlemen, without him? I hope you're working on your speech, Tim.
I've got
It's all
another really-
finished. It's finished.
Yeah, yeah. Jim Williams used to say, if you're going to give me 15 minutes, I'm going to need a 2-month lead time. If you need a half an hour, I'm going to need like a 2-week lead time. But if you want me to talk for forever, I'm ready right now.
Okay, so
We've
So
got
you're
two
gonna
of
take-
you, Jerry.
We got two Jerrys.
Oh, wow. That's interesting.
One's
Huh.
frozen, one's not.
Gemini.
are
You're a
you
Gemini,
talking?
huh?
Actually, he's a Cancer.
Are you with us, Jerry?
There we
he is.
go.
Yes.
You're closer.
Yeah, Ronnie, you're gonna love it, man. I'm gonna try to talk people into an 8-inch reflector being a good scope, but I'm gonna weave into that the Sea Star.
Okay. Can you see this share?
Yes.
Yeah, that's
Yes,
Okay,
and that is one beautiful picture.
that's the one from the UK, right, Jerry?
yeah,
Yeah.
it shows a beautiful summer solstice
Wow.
idea, the air. And this is
Yeah.
yesterday morning, 1 hour after sunset, looking west. Nice lineup of bright objects.
Yeah.
Spike, the moon. The moon's now up here a little bit.
Yeah.
Regulus, Venus, Jupiter, Mercury, and the twins down here just before setting.
Yeah.
Right. And Jerry, it's surprising you can still see Mercury. It's just amazing.
Yeah, if you have the right horizon.
Yeah. I mean, we were watching the moon basically walk through the planets last week.
Yeah.
It's really pretty.
Tom, when you're up there, and when you see Mercury, like when we looked at it with a telescope from the Gun Club, it
Mhm.
had scintillated into different colors, like a blue.
Right. Right. It's always close to the horizon, Tim.
Yeah.
So it's
Does
gonna
it
show
do
you-
that still?
That's severe seeing problems. when
Yeah.
it
Oh, okay.
shows different colors.
Yeah, it was really pretty though.
Well,
Yeah.
when Andy was showing Mercury at the star party, at
Yeah.
the museum star party, he has one of those little prisms that you can tune to tune
Yeah.
out the atmospheric refraction.
Yeah.
Oh,
Try and put the colors back together.
Yeah.
Yeah. And Ron, you know the definition of a prism?
yeah.
That's where they keep criminals.
Criminals, yeah.
Criminals.
Criminals. Okay.
Now, if you
Criminals.
if you take a picture of something like a star that's way on the horizon and it's got that scintillation of colors, it's blurred, it's red and green and yellow and stuff, and you can see the different colors. You can take it apart by colors in Photoshop, for example, other programs too, and then you can move them to align back up and you can put the thing back together. It's another way of taking the atmospheric refraction, differential refraction out of it.
Now, Chuck,
Like
you mentioned this thing that would tune it. I've never heard
Oh
of
yeah,
that.
Jerry, don't change it yet, okay?
I'm not.
Oh, go ahead, guys.
Okay.
Go ahead.
Oh, I was just going to mention yesterday we had a really nice group. We had 92 people come through and a couple of ladies speaking Albanian. It was really interesting. I
That's
asked them
what
if
it
they were
was.
speaking a Slavic tongue because there are all these nice whispering sounds. And no, it was Albanian. But the reason I'm mentioning don't change this was that the moon came up during the afternoon.
Yep.
Yeah.
It was absolutely beautiful. It was first quarter. It was riding right above the museum. And we just pointed it out to folks, looking at the sun through the scopes to take a look at the moon. It's really pretty. And I said, yeah, it's up in Virgo now. It went right by the Lion a couple of nights ago.
Tom Totten had another type of telescope out when your mount wasn't working, Jerry,
Yeah.
and we had the moon up. So he was looking at that while I was looking at the sun. We had it really going on that day.
Yeah. Yeah, a long time ago, when Tim and I started first working there, we'd often just get a nice look at the moon.
Yeah.
Okay, so we'd show people the moon. We'd peel off the solar filter, right, and look at the moon.
Yeah.
Now that scope not working, I learned something about my own scope and was
Oh,
embarrassed
good.
I couldn't get it working. But we got it aligned. Apparently during all of our trials, we had wound the scope up, and that era of astrophysics scopes did not have an internal wiring option where the wires go through the scope and get so they don't get wound up. So this one had buried in it, it had a factory set limit that you couldn't go around so many times to wind the cord up. And we had already done that, and we couldn't get it to move to the east because we had hit the limit for the cord winding. So we had to unwind the telescope, and then everything worked fine.
I'll be darned.
So we just backed it up. I brought it home over the weekend, and I cleared all the limits that you could put in, but this was a factory set limit, and I couldn't clear it. So that's what David and I figured out when we were there yesterday.
Is there any way to utilize the column to get it to kind of free it up?
The column?
Yeah.
No. It's
Can we
internal.
Can we bring it to the outside?
I don't know what you mean.
Well, so that if it winds up, you can see it.
Yeah, you can see it, and don't do it.
Okay.
Yeah.
Okay, this is looking now at the, in honor of our 250th anniversary, This is the night sky a little after midnight. Matter of fact, this is where it is about 1 o'clock. This is in the east. And you can see the Milky Way going through here, going through Cygnus. This is Cygnus as we see it up there. This program adds all these extraneous red lines here that are confusing. But I've been trying to go in there and modify it to my own custom thing, but it's not worth the time. So, but anyway, right in here, the North American Nebula, this is Deneb and the bright star in Cygnus. And right next to it is the Pelican Nebula. And this is those two nebula. This is the North American Nebula. This is the US up here. This is the Gulf of Mexico, Central America, South America. And this is the Pelican Nebula. There's the long beak. I just saw a very silly picture the other day on the internet. It showed a sparrowhawk with a big fish in its mouth flying around over the ocean. And right underneath the hawk with the fish was a pelican flying under with its looking up, and its beak was open. I guess waiting for the hawk to give it the fish or drop the fish or something.
Drop the fish, yep.
Yeah.
Yeah.
A lot of confidence in
And
that.
Jerry, a funny bird is the pelican.
Yeah.
Its beak can hold more than its belly can.
Yeah, I've heard that.
Yeah, it's Ezra Pound, I think.
It can hold in its beak enough food for a week, but I don't see just how the hell he can.
Yeah.
Okay, cartoon submissions are up front.
Well, that pelican could be the Atlantis, couldn't it?
Okay, now that we're gonna we spent part-time last week, and we talked about half of what I'd prepared on the Habitable World Observatory, HWO. And so cover it a little better and the parts we missed. So we're going to skip over some of this real quickly. But it's a part of NASA's large giant observatory program. And that program consists already of several satellites that were put up. And these tend to be the big money programs for NASA, aside from manned missions. This is, of course, the Hubble, which went up in the 90s. And this shows it being put into space with the Canadarm on the space shuttle. And then this is the Compton Gamma Ray Observatory, which was the next big satellite that was put up. And then we had the Chandra X-ray Observatory, which was a giant X-ray telescope. Found a lot of quasars and very interesting sources. Contributed a lot to the physics of star evolution. Then there was, let's get this bigger. This one, the Spitzer Space Telescope, which was a deep infrared telescope, the precursor of the James Webb. But it looked at a lot of things at what the resolution it could obtain with this relatively small mirror, smaller than Hubble or about the same size. I think the Hubble was about 80 inches or something.
94.
94, thank you. And this one's about the same. Then, of course, we're all familiar with this gigantic one, the James Webb Space Telescope, which had unprecedented resolution in the infrared and went out to farther wavelengths in the infrared and therefore required more cooling for its detectors. And this one used liquid hydrogen for its cooling. Should have turned that off. So this one is up there working away now in the L2 point near the moon. And this is one that is about to be launched. This is the Nancy Grace Roman telescope. It's a large visible and infrared telescope, mostly in the visible. It's got very wide field of view, and it will be launched soon. So that one is basically done. And then the next one is just this vague artist conception of the Habitable World telescopes. And it is it's shown here looking at Earth because it's trying to find other Earths. So far, our SETI search has focused on a couple of very weak criteria. That is stars with with a planet around it that's in the habitable zone. And that's pretty much it. So if it's in that zone, it could have a temperature that's okay for liquid water. But a lot of these things that we find are close to small red stars, and these red stars are very active. And so we're finding that blows the atmosphere away from the ones that are in its habitable zone. So we're looking for small Earths in a solar type sun habitable zone. And that's a much harder thing to do. Now, to understand what we're going to look for, this one we covered a little bit last week, but this shows basically the planets the exoplanets normalized to Jupiter's mass. So one here going across, this is Jupiter's mass across here. And the Earth is way down here, obviously lighter than Jupiter. But these are the planets of our solar system. This is if we were outside of our solar system looking for our planets. This is how they would look on this plot. So we're finding a lot of stuff up here. And what we want to find is a lot of stuff down here, an area we haven't been looking at yet. So this is going to be very challenging. They want to find extra Earths, and they want to find extra Earths that are like Earth now. But the chances of us finding an Earth that's exactly like us, that is, it has had the same 4.5 billion years of development, is quite slim. We might actually hope, that's the cleaning lady outside. So we might actually find the Earth as it was 1 billion years ago. The chemistry was different. The spectra is different. So we want to look at those things. So this thing plots Earth's timeline. So anything along this timeline that science tells us, modeling tells us will end up being a life-supporting Earth. Any one of those is in this pattern too. We want to find it.
So what they're going to do is they're going to kind of transpose what they see from how many ever light years away it is, and try to figure out what it's going to look like now based on different.
So they're going to compare it to Earth now.
Yes.
But they're also going to compare it to things that were Earth 2 billion years ago, say.
Yeah.
Cyanobacteria here, but no oxygen.
Yeah.
So that's in the ball game too.
That's smart. That's smart.
So anyway, this is a brief review of the Earth's major eras. Started with the Earth formed, the Earth's core and crust are formed, the Earth's first ocean formed. This is 4.4 billion years ago. It's 4,400 million years ago. This is the first life appeared on Earth, and this is not oxygen-breathing life. Here is oxygen began to accumulate in the Earth's atmosphere. The first animals evolved 0.7 billion years ago. Anyone got a question?
No, I'm just saying, boy, they're going to have to really bring it forward. Whatever they find, they're going to really have
evolution.
Yeah.
Dinosaurs went extinct, and then here modern humans evolved. And with this, we might get a chance of actually seeing city lights at night or hear radio waves, I Love Lucy alien version.
Well, so how do they tell the age of an exoplanet?
How do they tell the age of it?
Yeah, how long it's been there? How do they know?
That's a tricky question, and that's not what they're looking for, is how to tell the age of it. What they want to do is find it at any age. That, well, this isn't the Earth. Yeah, but this is how it's going to become the Earth.
Yeah.
It's not that they're after a certain number. Now, they've looked at the spectra of all these different planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And they've characterized them for composition. Of course, we're 78% nitrogen, 21% oxygen, less than 1% argon, and then less than 1% trace gases.
Boy, that's a narrow band there.
Yeah, but there's very interesting things about that.
Actually, Jerry, can you go back? I find it interesting that they're listing 42% oxygen for the atmosphere of Mercury. It's hard to read because it's blown out, for the colors.
Oh, I see. Yeah, 42%, yes.
I mean, it's a very, very small amount of atmosphere, but still, that's interesting.
In the real fine print up here, the atmospheric pressure on Mercury is 10 to the minus 14 atmospheres.
Yeah.
So that's like a fart. So anyway, Mars, it has 0.006 atmospheres. So it's still much denser than Mercury. But anyway, the way they're doing this is by looking at the atmospheres of exoplanets when it orbits its sun. So they look through the atmosphere as it goes behind the sun. They will get a reflection off the atmosphere here as it goes in front of the sun. They will get a transmission through the atmosphere. So they want to have it, and this is hard to do. It's very high resolution spectrometry, but they have found things, for example, H2O, or these speaks, methane, carbon dioxide. What is CH4 ammonia?
Methane.
Methane?
Yeah, of course. I just said methane here. Yeah. I had to listen to myself sometimes.
Jerry, what I found really interesting in the talking points, and I was going to ask you about it with the HWO, they have a I don't know what you call it. It's a blind that they put in front so they can see these really faint details of reflections, and that's going to be so important. But I
Yes,
don't
it
know
is.
how,
It's an
I don't know how
occultation disk.
I don't know how those work. Do you have any idea how those work?
Block the light of the star so
Yeah.
you can see the planet.
Now, is it just physically they move it in front of the star? That's it?
Yeah.
Yeah.
Okay.
Or they will have it rigid in the telescope, and they will move the telescope so that the disk is centered on the star.
Okay.
It's an
Yeah.
orientation issue.
It is. But it's really an important part.
It
It
doesn't
is-
help
it is
you
a key
when the
part,
planet's in transit, of course, but it helps you doing the
Yeah,
like
but you
orbital
also
phase.
get a little bit of it out here in the side too. So
Yeah.
But in transit, it wouldn't work?
No,
what?
because you'd block the planet too.
Oh,
Yeah, if you block the sun like here, then
Okay.
when the planet is in transit, it's blocked too.
I didn't think of that.
Yeah. All these things are being considered. It's very challenging.
Yeah.
The most important, let's see, this is the simulated Earth transmission spectrum as it would look at 0.03 AU. So about where the moon is, or farther. But this goes from this is wavelength in microns. This is 250 nanometers. So this is in ultraviolet. This is 500 nanometers. This is where the what is it? This is the green color, and you can see ozone here. This is oxygen out in the red, 600, 700. This is the red. And then at 1, we're in the near infrared. A lot of water vapor and methane here, and a lot of O2 out here in the short wavelength. Then methane, water, CO2, methane, water, CO2, methane. Now what they're looking for is things that are counter hostile to each other. I forget the term they used. But for example, to get O2 in the atmosphere and methane in the same atmosphere is a slam dunk for life, because these two cannot exist in steady state together. They attack each other. So that means that something is in there producing O2 and producing methane at the same time.
And just to clarify, this would be an Earth-like atmosphere on an exoplanet that's 0.03 AU away from its star, correct?
I think this would be 0.03 AU away from the Earth.
No.
Okay.
Because it's the Earth's transmission spectrum. So this is it if it were 0.03 AU away from
You're right.
the
You're
star.
right.
Yeah.
Yeah. This would be fairly close to the star.
Yeah.
So it's 0.03 away from the star, not us.
Not us. No.
Right.
Okay.
Chuck is right. It would have to be that way.
So the micrometers below where it says wavelength, and then it's mu m.
Yeah,
you have to
micron.
times 1,000. So that the 500 nanometers. It's times 1,000,
right here.
right? Okay.
Yeah, this is 5,000 angstroms if you're calibrated like I am in the old school.
Is that where our visual is around there?
It's where the sun peaks, roughly.
Yeah. Yeah.
And that's what we're looking at through with mirrors and with the telescopes, right?
Yeah, the sun peaks around 530 nanometers.
Yeah.
Okay.
So we see from about this dip to about 0.75 is a little long.
Yeah,
that's visual there.
Yeah, right
Okay.
there.
Good.
And then this is stuff that requires cold detectors.
Oh
But
boy.
out here at 2.5, these are short wavelength detectors. They do not require ultra cold like James Webb does.
Oh, they do not.
Now
Oh.
this is the what Earth spectrum looks like in an overview, and what they're looking for right now. They're looking for the oxygen methane disequilibrium. So you can't have them both in equilibrium at the same time. So if you see both of them together, that's taken as the biosignature.
Interesting.
Of active replenishment by life.
That's neat, Jerry.
Yeah. So they're looking, now they find water vapor, deep absorption bands indicating liquid water, oceans interacting with the atmosphere, if they see that. And then the vegetation red edge, VRE, a sharp rise in reflectance in the near infrared spectrum caused by chlorophyll-bearing surface plants.
Oh.
And let me show you that. This is an example from a Landsat satellite. And this is tuned for seeing crops. And this is the red edge here. And this is these are one of the first satellites put up around Earth back in the 60s, the Landsat series. And this is so important for you'll never guess what industry, but it is key to that industry. And so the Congress passed a rule that as each Landsat generation disappears, or its operational life expires, another one that operates exactly to the same sensitivity and the same wavelength and the same optics will be put up to replace it. And that's what's been going on. It's a very unpopular satellite to make because there's not a lot of profit in it. They thought they were going to sell these pictures for quite a bit of money. As a matter of fact, back in the 80s, if you asked for your property to be photographed in this way, it would cost you $50,000 for one photograph.
Oh God.
But the industry that uses this is the finance industry. And what they're doing is they're placing it's in the, what is that called? The market where you
Futures?
Futures, thank you. It's like you can look at the wheat fields. You can tell whether it's in trouble this year or it's going to be abundant.
Can they see petroleum or gold or stuff like that?
Nope, can't see any of that. This is purely biological.
Okay.
There are other satellites that look at landforms that people think they have found the key to those things under the ground, but it's hit or miss.
Okay.
But you can find golf courses like you see up there in that one.
Yeah, there you go.
So right now, before we have the habitable worlds things, we have found M dwarf planets. And it always confuses me because Star Trek had an M-type world, but it's really M-type stars. So around an M dwarf world. But it's being actively, they're like TRAPPIST-1. And then the JWST suggests some of these inner rocky worlds, for example, may have had their atmospheres completely stripped away. So we're just on the fringe of determining some of these things. Early Earth analogs, some young, highly irradiated super-Earths are showing signs of heavy secondary atmospheres rich in CO2 or water vapor, resembling early Venus or primordial prebiotic Earth, other than our modern world.
Jerry, from your previous slides, when it showed the atmosphere and what was in it, that was a very narrow band that had the right gases in it. And then considering what they're looking at here, we're going to maybe be a little harder to find than we thought.
I think it's going to be very hard. The aperture of this thing is going to be 6 to 8 meters. So it's going to be a big telescope.
Yeah.
Now, this, for example, are two representations of the Earth being looked at by the James Webb. This is the early Earth, prebiotic. This is the present Earth. So it has water vapor, oxygen, and methane. Here it has methane only, no oxygen. So this would be early cyanobacteria or no life yet.
But if we saw that, it's a good sign.
Yeah, that would be a good sign. Now, the ones that are real interesting now are TRAPPIST-1. This is what it looked like. Oh, the dates are gone. But this is what it looked like back in the when it was first discovered, I think in the 80s. And now that James Webb has looked at it, we see that it has many more Earth-sized planets, but only these are in the
Habitable zone.
Yeah, Goldilocks zone.
Yeah.
So that's really all we know about it. And this is not a good candidate.
And the TRAPPIST was where, Jerry? I'm sorry, I'm blanking on it.
Southern Hemisphere.
Okay.
I don't know if I have a chart in here that shows that. But anyway, this is a planet, a giant, gas giant, hot exoplanet WASP 39b. And it's got a very strong carbon dioxide band out here in the infrared. 3 microns to 5 microns. This is MWIR, MWIR. So we won't see any of this in our telescopes. But it's a and this has been fairly well characterized, but it's a good atmosphere. We can see light coming through and from the atmosphere with present equipment.
And I throw in a question that's not exactly on the topic, but it's similar. When the Huygens went in on Titan, did it find amongst all that methane any oxygen?
And a lot of methane.
It was all methane?
No, part ethane.
And
Okay.
nitrogen.
But no oxygen.
No free, not much free oxygen, if any.
Okay,
Yeah.
we just lost Tom.
Yeah, Tom had to take off.
Okay, that's fine. Wow.
Oh, yeah.
Okay.
Okay. This is another promising world that will be among the first targets studied in detail by the Habitable Worlds Observatory. James Webb has detected water vapor and carbon dioxide in the atmosphere of exoplanet K2-18b. Now, this is the one that had, I think, the chemistry, I forget the chemical compound, but it's very debated whether it's a property of water world or not. But it doesn't show on this chart. This very strong H2O. So it's got water and it's got CO2, but and the visible is shown really clearly on this one. So this is 1 micron. That's where silicon really cuts off. So from this right there, the purple to just short of 1, right about there, that's what we see. The rest of this red here is near IR. And then at 1.4, you're starting picking up the short wavelength. This is where fiber optic communication operates in here. It's not friendly to our atmosphere. We send it through fiber optic light guides. Now, one of the problems that they're looking at is just like we do with our astro-imaging, is that every time you take a picture, and this means with your cell phone at a baseball game, you're taking a picture of all sorts of things. You're taking the object plane, which is things you want at night, you want stars. Things you don't want is like airplane, meteors, street lights, all sorts of crap from inside the telescope. And so a small part of this frame is what you want. Now, when you take a picture during the daytime, this is so much brighter than anything else that you don't even worry about taking these things away, doing any kind of image processing. But when you take pictures that take 10 minutes to an hour to get the object to show up in the night sky, then you're letting these things come in like gangbusters. And so you have to perform steps to take these out of your picture. And this is what they're going to face with this new satellite for habitable worlds. First of all, there's the flat frame, which is any non-uniform illumination that's going to screw with your quantitative brightness measurements. It's due to vignetting, dust, plus non-uniform sensor response. And all that is taken by making a separate photograph of that. You look at some blank, you don't look at the stars, you look at you look at a blank white field, like a white t-shirt at night or a white card.
Oh, okay.
Photograph that with the same exposure time that you would for your regular shot. And then all those crappy things will show up.
Interesting. Those are those questions I keep asking you over and over.
Yeah.
In the workshop.
Now, this is a pattern of that blank white frame taken by the Cassini spacecraft using Titan as its back white frame. So it's looking at a blank cloud top of Titan. And this is what the field looks like. These circles here are called dust donuts, and they're out of focus dust things on the optics on its way to the focal plane. This is a highly exposed hot pixel that is resetting the zero for its neighbors. Thank you very much. So this is a defect in the focal plane. So you want to correct for all these other things. These circles are other dust things on other planes. And then you see it's darker at the edges. That's vignetting because not all of the focal plane is looking through all of the aperture. So
Jerry, how do they subtract that?
Good question. Good question. Easy done. It's easy done. Virtually every form of photo processing has a place where you store your frame that you want, you're interested in, and then you store, this is what would be called a master light frame or a master flat frame. And then it does a pixel by pixel subtraction. If it's real bright here, for example, 1 pixel, can I blow up to see a given pixel? Close.
Oh, yeah.
For example, there's a real bright pixel up there. And you look at your pixel, one of these pixels has a coordinate position. And so you look at pixel number 1075, 50 over there, and then you look at the same pixel in your photograph, and you subtract the amplitudes of the two signals, and there you've taken this frame away from your frame.
But if these hot pixels have saturated, then you'd have to do some kind of averaging of the pixels around it.
Yes, you can do that. That's called a dark field mapping. This is the traditional way to do it. This is answering or commenting on Chuck's correct pointing out. This is the dark frame. This is where you take a picture of what the camera sees with no light coming in. So just because the detectors are actually electronic parts, they're diodes, and they're going to have some kind of electrical activity all on their own, and they're going to emit new electrons, but electrons that were not excited by light. So you don't want those. You want to get rid of those things. So you take a picture of the thing here with the lens cap on, and you can see which pixels are bright. Those are short circuit pixels, and then you subtract those out of there. But what Chuck
does heat play a part, Jerry?
What's that?
Does heat play a part in this?
Heat, yes. This temperature, the dark frame, is showing the dark current, and not dark noise. It's showing dark current. These are all things that can be subtracted. These are all signal you're not interested in. They're not noise. They're signal you're not interested in. But the dark current coming out of a detector is dependent on the exponential power of the temperature. So if you add 10% to the temperature of your focal plane, you get maybe 20 or 30 times the amount of dark current from that pixel. So you want to take this frame and the flat frame and the dark frame all at exactly the same temperature.
Oh,
So
interesting.
it's very hard with DSLRs and cell phones because you don't have a temperature monitor for the focal plane. But
Yeah.
specifically made astro cameras are super. They're cooled by Peltier coolers and right to the exact same temperature to control that dark current.
Wow.
Now there is in everything there is noise. So in the dark current, there is a noise in the dark current. But noises, you can't subtract the noise because they're a temporal fluctuation. So the dark current from one pixel would be jumping around all the time. And when you take a picture of it, it's frozen. Take a later picture, there's another value, but the difference is extremely small. And so that is largely ignored. The word noise is usually incorrectly used for anything that annoys you in the picture, whether it's noise or signal. My favorite example is that you're laying on the couch on Sunday afternoon and you're trying to take a nap, and the kid next door is trying his new violin. It's really annoying, and so that is in physics, that violin noise is an interfering signal, but to you, it's annoying noise. So there's a lot of things like dark noise is let's see, what is it? Fixed pattern noise, which is an oxymoron all by itself. That's not a noise. That's an artifact you can subtract.
So with this particular type of noise, you can't close a window on it, right?
No, you can. There are ways to get rid of the noise. The ways to get rid of the interfering signal, like closing the windows. But here you just subtract it, like these earphones that take away the sound outside. They're subtracting that kind of noise. It's not noise, it's just interfering signal. But so that you take away that, then there's the bias frame. This is non-uniformity in the circuit of the camera from the amplifier. After the picture is taken, it goes through an amplifier to go to the memory. So that you characterize that by taking a bias frame, and you take all these things away, and that gets you the final image that you're going to use. Now, for real noise, if real noise is a problem, which it usually is not, then what you do is you don't take it away. You can't characterize it because it's a time fluctuation. So you add more noise to it, and then it changes the signal to noise ratio in favor of the signal, because signal accumulates, signal adds, but noise root sum squares, which doesn't go up as fast as the signal goes up. So you improve signal to noise ratio, and that's how you get rid of noise. The way that you do that in our astro images is you take maybe 25 subframes of something and then you stack them. And that's a method of increasing the signal and noise. Yes.
I want to ask Ronnie, in your radio career, did you have something similar to this when you're transmitting, or
pixels?
you could filter out noise?
I'm sure they did, but I wasn't in the transmitter.
Yeah, they have a control thing on radios called squelch, and it's a way of filtering noises.
I got to tell you, I sat in a studio once with a 50,000 watt transmitter less than 10 feet away on the other side of the glass. That's as high as you can go in this country, 50,000. And I could hear myself and my music. My whole radio program was on my teeth.
Oh,
because it would feed these directional antennas. What I need to know is some basic stuff real quick, if you can answer me real quickly. Pixels are like tiny little bulbs that if you magnified them, would they look like light bulbs?
Yeah, take a magnifier and look at it.
Are they light sensing?
Can you see this? Probably no, it's going to be background.
I see a white, and I see something on the screen.
Yeah, these are actual microphotos of pixels. Each pixel, when you look at the there's pixels coming in, pixels in the camera, which are not called pixels because there's no picture yet. Pixel stands for picture element. So when you look at your TV, there's a pixel, and the pixel is either red, blue, or green. If you look real close, and they're right next to each other, and they give the eye, they blur in the eye to make the colors. And your eye is not very sharp with colors. It's real sharp with black and white. So we generally process astro images, getting the brightness or the resolution in the luminance frame, which is the black and white frame. And then later you add red, green, and blue to it, and you get the color image. It's like a kid with a coloring book. Your eye is real tolerant of coloring over the line. You can't see it. So you can take a real quick color picture that's very blurry, and you put it on a real sharp black and white picture, and it will look like sharp color.
Can I make a really silly comment here? When I lived in an era where black and white TV was it.
Yeah.
And when I saw the first color TV and I watched it for an hour, I was really tired. I got really tired, and I'm not really sure why that is.
Well, I can tell you exactly why that is, but it takes a long time.
Okay.
When I first hired into Hughes Missile Systems Group, they had a missile that they launched called Maverick, and it was a TV guided missile. And you see the TV display in the pilot's cockpit. And we wanted to change that. We were developing infrared guided missiles, and so the infrared systems at that time were scanning systems. They weren't simply a chip that measured things without moving. They weren't two-dimensional like that. So it was a scanning system. So you had to convert the scanning system of the infrared camera to the display system of the TV in the cockpit, which is 525 lines. And if you ignore human physiology like that, you create something that pilots can't look at. Not only do they get tired and put to sleep, but looking at some displays that are not careful about how they display, it actually becomes painful to look at it.
Ooh.
And after a while, your eyes will look away automatically to avoid it. You can't make them look back.
Wow.
So we had to study a long time how we do, because you have much fewer scans with the infrared and many more with if you do simply add them together, it doesn't work. You have to take into account the timing of how the eye is expecting to see, because when we see motion, we get we're looking at a bunch of stills and we put it together, our brain does. And if it comes at it the wrong way, your brain gets confused and can't do it, and you avoid it. But that's where I got drilled into my memory that the exposure time of your eye on a bright day is 0.04 seconds.
So interesting.
40 milliseconds. That's when you look at the world, your eye is taking a still frame every 40 milliseconds. Your brain puts it together as continuous motion.
Well, can I just throw in one quick question that I've always wondered and see what you tell me? Are each one of these pixels on the big screen, and there's jillions of them, connected with a wire? Each one has a little dinky wire going to the computer?
They're not wired like that. They are connected, but they're connected by microcircuits. For example, the detectors we make, I'll show some pictures next time, but we have 2 layers of material on a donor type material, on a acceptor type material, semiconductors, same semiconductor, silicon. And then we go in there with an ion beam milling, and we make little mesas out of the whole array. It's an array of mesas. And the bottom layer is continuous. So it connects to every element. The top layer has to have a little bump on top that's made out of indium. And then for our case, the circuit that comes down is also cut into mesas like that, and it has a bump on top of it, and the 2 wafers are smashed together, so the bump to bump connects, and that's where you connect to the top of each mesa for each element. And then that goes through the circuit on the top layer that goes out to the side. but it's not a wire. It's a thin strip of conductor that's laid down, copper or aluminum or silver or gold, usually gold.
But it's analogous to a wire.
Yes, it performs the same function as a wire.
This micro technology is really great because I mean it's otherwise you have these really tiny people working on these.
Yeah, they don't drink much coffee though. There's a lot of coffee around.
Well, I wonder if you could compare it to Christmas tree lights that are either in parallel or in series.
Yeah, if you look at you go to a baseball stadium and there's a big scoreboard over there, but it's not a scoreboard, it's a collection of clusters of red, blue, and green light bulbs.
Yeah.
But it's so far away you can't see individual light bulbs. But you power it, it's basically a TV, because it shows the same image. You power it with the same electronics you'd run a TV with, and it shows you a big image.
If
This
you
is good
came
stuff,
in
Jerry.
close, if you came in close to the screen that you're talking about, that's filled with these pixels, even with a magnifying glass,
Yeah, you can see them easy with a magnifying glass.
you could.
Yeah, the best magnifying glass you can get is to look through a high-powered eyepiece backwards. It makes a wonderful microscope.
Oh, I didn't know that.
Yeah.
Supposedly the new Vera Rubin telescope in South America has 1 million pixels.
That's big. They take a picture all sky every 2 nights or every 1 night or something, and they're looking for things that are moving, things different from night to night. They've found thousands. The other telescope that went up that has that camera like that went up and it's an observatory. It's not in orbit, but it found thousands of new asteroids.
The Vera C. Rubin, on the first image found like 11,000 asteroids.
Yeah.
New asteroids.
Yeah. Yeah. And that's an Earth-based telescope.
In another sense, Chuck is probably going to be talking about one facet of that in December.
Okay.
Well, I don't know. You use just a regular camera to do your occulting, don't you?
Well, it's a little video camera, yeah.
Okay. How many do you know the number of pixels?
Oh, it's like 1400 by 1400, something like that.
Okay. That's
Gonna
on
be
the
interesting.
side.
It's gonna be
Yeah.
interesting.
Multiply those two. Well, I got lost a little, but I caught up, I think. And I'm looking forward to you guys' speeches in December, and I wish I could find somebody for October.
Yeah.
Want to thank the president for covering August. And let's do it again next week. Maybe all 5 of us, because members board of the Santa Barbara Astronomical Unit just can't get enough of this cutting edge cosmology.
I found this very interesting, Jerry.
Yeah,
Thank you.
go online and learn about us, SBAU.org. That's number 278. Next week, number 279.
Okay.
The Santa Barbara Astronomical Unit Astro Hour. We'll see you again. Thanks, everybody.
Live long and